To develop a language of time complexity, we'll introduce a complexity function. Generally speaking, given some problem where we can describe the input size as a positive integer n, the complexity function outputs a positive real number fn. We can interpret the complexity function as the number of steps required to solve a problem of size n. And for convenience, we'll omit any rounding rules. For example, the binary search on an array with n elements takes time, ceiling log 2 of n, find the corresponding complexity function. And remember, the ceiling function was introduced because the number of steps had to be a whole number. We typically omit the rounding rules, so Tn is log 2 of n. Now consider two algorithms for solving the same problem. Suppose the first requires this many steps, while the second requires that many steps. Which algorithm is faster? And the answer is, it depends on the size of n. The first algorithm is going to be faster whenever the number of steps is less than the number of steps required for the second algorithm. Well, that's an inequality, so we can solve it, and we find so for n greater than 10,000, the first algorithm is faster. And a useful idea moving forward, go big. While the second algorithm is faster for smaller values of n, eventually the first algorithm is faster. And since we generally use computers on large inputs, we generally regard an algorithm as faster when it is eventually faster. In other words, we want to know what's faster for sufficiently large inputs. What about an algorithm that requires 1000 n squared steps? Now, we find that the quotient of the number of steps between the first and third algorithm is 1000. So for sufficiently large n, this algorithm will take 1000 times as long as our first algorithm. While we might view this as the third algorithm being much slower, we might not notice the difference. Suppose the first algorithm requires 1/10,000th of a second to solve a problem with input size n. If our second algorithm takes 1000 times as long, that's only 1/10 of a second, and in that case we might regard both algorithms as fast enough. In other words, from a practical standpoint, even though the third algorithm takes 1000 times longer, conceivable increases in processor speed will make the difference in time unnoticeable. And this leads to the following idea. Roughly speaking, if one algorithm takes c times as many steps as another, then on a sufficiently fast machine, the difference in runtime between the corresponding algorithms is negligible. In this sense, all three of these are the same type of complexity function. And without too much imagination, we can find others that should also be the same type. For example, since these are all quadratic functions, we might say the corresponding algorithms have, let's think of a good name for this. How about quadratic time complexity? We'll use the notation theta n squared to indicate all time complexity functions with quadratic time complexity. Intuitively, we might expect some steps, such as addition, to take less time than others, such as multiplication. And while we typically disregard storing and retrieving data, we might imagine that these operations take some time as well. So why can we treat all the steps as being equivalent? Well, let's think about this. Suppose a problem requires fn steps. We can imagine splitting our function into the additions, multiplications, decisions, and so on. So our function is a sum of other functions. Now, suppose it takes some amount of time to perform an addition, to perform a multiplication, to make a decision, and so on, then the actual amount of time it would take is going to be Now we can look at the ratio of the actual time required f star to the number of steps f of n. And we want to know what happens to this ratio for sufficiently large n, so we'll take the limit as n goes to infinity of that quotient. Now, we'll assume f is a polynomial. The proof is similar for more general functions, but we'd have to introduce a lot more terminology to talk about them. Since fn is a sum of other functions, then at least one of these has the same degree, and none can have higher degree. And what that means is that f star also has the same degree as our original function. And since f star and fn have the same degree, then the limit as n goes to infinity of their quotients is going to be some constant c, which will be the ratio of the leading coefficients of the two polynomials. So this means that for sufficiently large n, the actual time f star will be about equal to some constant multiple of the number of steps. And so the actual time complexity is still in the same complexity class. And what this means is that while we could incorporate the actual time required for the different types of steps, it's not worth the extra effort, unless it is. Well, it generally isn't, but eventually we might care.